In this recording, I'm going to talk about one of the most important topics in the geometry. So in this video, we're going to touch the symmetry in the 2D shapes and rotational symmetry in 2D shapes and the plane symmetry in 3D shapes. At the end of this video, we are going to talk about some diagonal properties in quadrilaterals. So we're going to start with the symmetry first. So we have here a perfect heart, that's sketching. So we are interested in whether we have a line of symmetry for this shape or not. So just quick reminder, the line of symmetry that is the line that perfectly divides the shape into two equal parts. So when you fold this shape with respect to the line of symmetry you sketch, each part perfectly fits each other. So for this heart, this shape, the shape on the screen is symmetrical. Reason, if we sketch the line that passing through that shape, so each of these parts, when you hold it, perfectly fits each other. So that line called line of symmetry for this shape. And this shape is symmetrical. So we have only one line of symmetry for this. And that's the only one. If you check with the other lines, let's say, goes through like this or like this. So when you fold this shape after you sketch your line, it's not going to be perfectly fit into each other, each pieces. So for some shapes, we have more than one line of symmetry. For example, here we have a compound shape. So obviously, first line of symmetry will be this. So if you fold this into this piece, it will perfectly fit. So the second one, probably you already guessed, will be that line. So because when you fold this piece after you cut using your symmetry line, will perfectly fit into this piece over here. So that shape we have here got two lines of symmetry. Let's have a look at this. Well, so we are interested in here, how many lines of symmetry does this shape has? So the first line of symmetry is the line that passing through vertically over here. So obviously when you fold this shape, this part we cut out, into this part, with respect to the line of symmetry we sketched, it will be perfectly fit. But that's not the only one. We have one more. And you can see now also this part of this shape perfectly fits to that part if you fold with respect to this line. And we have one more. So overall, the shape we have on the screen got 3 lines of symmetry. Let's have a look at pentagon. So that's a regular pentagon. So the regular pentagon got 1, 2, 3, 4, 5 lines of symmetry. So as just its number of sides. So if you go back, look at the first one. If I fold that piece into this with respect to the line of symmetry it's given, it will be perfectly fit each other. So I can do the same with that line as well. Same with this, and same with this line as well I can do. So altogether we will say that this shape has 5 lines of symmetry. So have a look at the circle. So how many lines of symmetry we have in the circle? So for the circle that you need to remember, we have infinitely many lines of symmetry. And you can sketch infinitely many lines through the center of circle that each piece will perfectly fit each other. So you can cut the circle infinitely many into semicircles, obviously. So I hope you already got what is the line of symmetry. Now we are moving rotational symmetry. Rotational symmetry for kids, for students, is quite confusing because you're rotating shape and just checking how many times the shape when you're rotating 360 degrees fits into itself. And this is quite hard, like quite hard to do mentally. And when the shape is actually a compound, like some complicated shapes they're given, it will be really difficult. But if you get the main idea, I hope you can do that. So we're going to start with the example. Here we have a shape. And we're looking for how many lines of symmetry first we have. Just a quick, gonna go through the line of symmetry. And then the next we will look at how many rotational symmetry we got. So there are no line of symmetry for this shape. So there is no way that you can sketch a straight line or vertically or horizontally or diagonally that when you fold with respect to that line that fits each other, this shape, each piece fits exactly precisely into each other. So we don't have this. But there is rotational symmetry. So we'll look at how many rotational symmetry we have for this shape. So for this, usually the way I do, I just denote the one. It doesn't matter, you can just cross X over here, over here, over here. Usually I do it on the top of the shape. And then I'm going to rotate this. So while I'm rotating, I need to keep my eye on how many times while I'm just rotating 360 degrees, how many times this shape looks as it is, I have here. So if I do this, it's 1, 2, and 3, 4 times. When you rotate this, I'm going to rotate one more. This shape exactly fits into itself 4 times when I rotate this 360 degrees. So we're going to say that this shape got 4 rotational symmetry. And let's look at one more. So with the first question is how many lines of symmetry we have. So here is the first lines of symmetry. So hopefully you can see that if I fold this piece that I cut out into the piece over here that I cut out using the line of symmetry, with respect to the line of symmetry, I'm folding this, I will precisely like fit this piece into this. And this is not the only one. We have one more that I can do this process. I can just fold this piece into this. It will perfectly fit with respect to this line of symmetry. So I will say that there are 2 lines of symmetry I have. So but how many rotational symmetry we have? So I'm going to put the cross, and I want you to keep your eye on the cross and keep your eye on the shape, how many times the shape exactly the same as it is. So this process is 360 degrees. I need to rotate it until the cross that I put over here is coming back to itself, the place it was, let's say. So this is the first, and then this is the second. I will rotate it one more. This is the first over here, and this is the second one. So we will say that this shape has 2 rotational symmetry, or rotational symmetry of order 2. So let's have a look at hexagon. Or this is octagon. So how many lines of symmetry? So normally for the polygons, like starting from five-sided regular polygons, pentagon, hexagon, heptagon, nonagon, decagon, because we have the lines of symmetry as a number of sides. Okay, so if you have a pentagon, we will have line of symmetry 5, a hexagon line of symmetry 6, and so on. So the first line of symmetry will be this. As you can see, this part of the shape perfectly fits that part. And this one, the second line of symmetry, third, fourth, and the final one. So we have here 8 lines of symmetry. So we do know that, like, we can cut this into basically using line into 8 pieces that we can fit perfectly to each other. So, but how many rotational symmetry we have? That's the question. Of course, I will put the cross on the top. You can put it over here. It doesn't matter, over here, the top, any part you want here, of course. So then we're gonna rotate, and we have to keep eye on the shape until we have done one complete rotation. So how many times this shape fit into itself? So this is the first, second, third, fourth, fifth, sixth, seventh, and eighth. So one more. If you just look at the shape carefully, you will see that this shape, while I'm rotating it 360 degrees, fits into itself 8 times. So the order of rotation, rotational symmetry will be 8. So as you can see, rotational symmetry and the line of symmetry for the polygons, starting from 5 sides, is just the same. So I hope you already got what is the rotational symmetry and order of rotational symmetry, basically the same. So we're gonna look at some symmetry properties for the quadrilateral. So square got the number of lines of symmetry 4 as the number of sides, and the rotational symmetry also 4. So the rectangle got 2 lines of symmetry and 2 rotational symmetry, as you can see. Let's rotate it one more, 1 and 2. So don't forget, so we rotate the shape 360 degrees to count how many order of rotational symmetry we have. So for a parallelogram, we have 0 line of symmetry and 2 rotational symmetry, as you see from the rotation. So for kite, we have 1 line of symmetry and 1 rotational symmetry. It only fit into itself at 360 degrees. So we're not going to say it doesn't have rotational symmetry. We will say it's got 1 rotational symmetry. So for the rhombs, we have 1, 2 line of symmetry and 1 and 2 order of rotational symmetry. So that's it for the quadrilaterals, the line of symmetry and the rotational symmetry. Now let's look at a plane of symmetry. Plane of symmetry is obviously going to be on 3D shapes because we're talking about plane. And the plane of symmetry is the idea that you can divide 3D shapes, just like 2D shapes with a line of symmetry dividing into 2D, 2 pieces that fit into each other. So the plane of symmetry is the plane that divides the 3D shapes into 2 pieces, that each piece, when you just put them, put one piece into the other, inside the other will perfectly fit. For example, so here we have some planes that cut this 3D shape, so we need to identify which one is the plane symmetry, which one is not. So obviously the first one is not, because that piece is smaller than the piece I have on the top. For a cylinder, Okay, so for the triangular prism, it's perfectly like divided into uh, two pieces, two equal pieces. I can take this piece and perfectly fit into that piece I have here. So as you can see for the cylinder over here, I have a plane of symmetry, that one that cuts this plane of cylinder into two pieces, that piece perfectly fits the other. And for the rectangular pyramid, it's not the plane of symmetry, as this piece obviously not going to be the same as the piece we have over here. And this is the frustum. Basically, we have that topic in 3D shapes. And obviously, like on the top, we will have a pyramid, the cut part. But on the bottom, this is not a pyramid. This is called a frustum. So let's just investigate how many planes of symmetry are there for cuboid. This is the first one. As you can see, that piece over here, if I put it here, perfectly fits into that piece that I cut out. And this is the second one. As you can see, I just divided, like this piece fit into this. This is the third one that I can divide, obviously, like this piece, sort of the back of this plane, perfectly fits into that piece. So we will say that then for cuboid, we have 3 planes of symmetry. So the plane of symmetry is that basically the plane that we're using to cut out the shape, that the pieces we have fits into each other. Okay, somehow look like these line of symmetry in 2D shapes. So after just found out how many plane of symmetry we have for a cuboid, now we're gonna look at cube. So cube got obviously 9 planes of symmetry. So the first one, this piece over here, perfectly fits the piece on the bottom we have cut it out. And obviously this one, so sort of like just diagonally cutting the shape into 2 parts, the cuboid. And if this is true, the vice versa is also true. And other one, so the vice versa for this, vice versa for this. So this is the vice versa for this one, just sketching the plane of symmetry using this edge over here and the opposite edge right here on the base. And the same over here with this. And we can have this one, obviously, just this piece over here. Cutted pieces here, triangular prism, fits the other one. So, and I can do it in this way as well. So you can just perfectly say this piece perfectly fits the other, and so on. So overall for the cuboid, we have 9 planes of symmetry. So I hope you got the idea with the plane of symmetry, because it's almost look like the line of symmetry, but it's a 3D shape. We cut this the shape with using the plane. It's just you're using a knife to cut the cake. You cannot use a line to cut the 3D shape because it's in 2D dimension. So what about a diagonal property of quadrilateral? So note that understanding the intersection of diagonal properties is essential for the later topics in shape and space. So try to understand it here or memorize it here. So for the square, we have 2 diagonals. What's diagonal, if you're gonna remember that? So it's going to be, the diagonal is a line that connect or join 2 vertex of shape. So some shape doesn't have diagonals. For example, triangle doesn't have a diagonal because there is no way to connect using a straight line to two vertex of this triangle. But there is diagonals for a square, for quadrilaterals, for polygons, pentagon, hexagon, and the others. So we're gonna say that diagonal of square bisect each other. So the bisect means divides each other into equal pieces. two equal pieces, and as well as we do know that the diagonal of a square are equal. Diagonals of square are equal. So, and in the intersection point, the diagonals, they intersect at 90 degree. So for the rectangle, the diagonals also bisect each other. And by the way, just like a square, diagonals are equal. And the only difference is at the intersection, they're not 90 degree. So intersection of diagonals, they're not intersect. Diagonals don't intersect at 90 degree. So for the rhombs, diagonal bisect each other, but they are not same. Diagonals are not same. But just like a square, they intersect at 90 degree. So for a parallelogram, diagonals also bisect each other, not same. Their diagonals are not same, as you can see that this line over here longer than that we have, and they don't intersect at 90 degree. All right, so I hope you enjoy, I hope you learned. Have a good day. See you in the next video.